All right, so the third speaker in this session is Vahab Mirrokni, who will be talking about large-scale clustering in MapReduce and beyond.
Thank you. Thanks for having me. So yeah, I'm going to talk about large-scale graph clustering in MapReduce and beyond. I'm going to mention results from several papers and several joint work recently with different groups of people. I'll focus on the new work that are basically the three new ongoing work, one of which appeared in ICML and two of them are ongoing. So let me start with the first slide with some takeaway messages and the goal of the talk. My goal, we are building a group of project in New York and with collaboration with other places at Google. Our goal is to develop a graph mining tool, library that works with very big graphs, Google scale graphs. We are talking about trillion nodes and tens of trillion edges. But we want to only work with fault-tolerant existing systems like MapReduce, Pregel, and a new graph mining framework that we call ASIMP. I'll mention throughout the talk. So the problem that I'm trying to solve throughout the talk is what I call overlapping graph clustering. So I'll try to focus on algorithmic ideas instead of reporting running times and so on, which is maybe not fair to compare with the existing work outside. I'll try to report some relative running time, but then I want to deliver different algorithmic ideas. For example, I want to talk about local random walk-based algorithms to compute well-connected clusters. Some ideas about better MapReduce-based algorithms with the use of in-memory service and an asynchronous message passing graph mining framework that we have been working with for the last couple of years. So I'm talking about graph clustering problem. So you know you have a set of entities, you have similarity between them, and the goal is to find good clusters of similar images. The first question is how can I, and this has application in several areas. The first question is how can I basically capture this in a metric? So the popular metric that people use is what we call graph conductance. Basically, this is, you want to find a set of cluster that has a small number of edges going outside. Basically, we want to minimize cut conductance, which is the cut edges that we have for the cluster over the total volume of the cluster inside. So this is the number of edges that are cut. So in this case, we have a cluster with 2 edges in the cut, and then we have the total volume of the cluster in the denominator. So you may have heard of, have seen this objective function. So this is basically the total volume that's inside the cluster. So that's basically the sum of the degrees of the nodes in the cluster. The problem I'm trying to solve is not only finding one cluster. I want to find overlapping clusters in the whole graph. So the motivation behind overlapping clusters is known to all of us. Natural social communities have this property. You can find better clusters using overlapping clustering compared to partitioning. They're easier to compute, and they can be used to accelerate distributed computation. If you store your graph into several machines, if you do overlapping clustering, it may help you in communication cost. So let's say the good clusters that we want to find are clusters with low conductance. If I want to formalize this problem as an optimization problem, I can say I would like to basically find a subset of clusters or basically a subset of nodes in the graph. Each of them should have basically volume at most B. And we have to cover all nodes in the graph, or cover almost all nodes in the graph. And the goal is to look at these clusters and find some quality measure on each cluster and optimize the vector of qualities. So for example, we want to minimize the maximum conductance or minimize the sum of the conductance or minimize some norm of the quality measure over the clusters we find. if you think about approximating these type of objective functions, there are probably logarithmic approximations, and it's better to use overlapping clustering compared to non-overlapping clustering. But here we want to talk about how to do these things at very large scale. So the way that we find these overlapping clusters is to apply a two-stage type algorithm. The first stage is we produce local clusters around nodes, across the whole graph, around the seed set of nodes maybe, or across all nodes in the graph. And there we use local message passing algorithms to do that. And then we take these local clusters, these are candidate clusters, we build another graph over these clusters, and we get rid of overlap. We merge some of these clusters to get rid of too much overlap to come up with a good overlapping clustering of the whole graph. And this has been used in some papers. Maybe I'll mention if I have time at the end. Yeah. So the next 10 minutes each, I want to talk about local clustering, how we do local clustering in each, from each node in the graph, some algorithmic ideas and some ideas we use in practice, and then how to generate basically an overlapping clustering out of these local clusters using more global clustering ideas. So first, let's talk about local clustering. So when we talk about graph clustering, for example, to find good conductance cuts, this is a major research area. There are different type of algorithms that have been developed. For example, there are spectral clustering algorithms that achieve a square root of the optimum that's available, the optimum solution that you can find. There are logarithmic approximation based on combinatorial ideas, and there are algorithms that are based on semi-definite programming, and they give better approximations. But these algorithms are all global. So here I'm trying to develop some local algorithms. Let's understand what we mean by that. So global algorithms, the running time may be linear in terms of the total size of the graph, but they may be the size of the graph might be much bigger, much larger than the size of the cluster that we want to output even. So what do we mean by local clustering? We want to find an algorithm that has this property that the running time of the algorithm should be a function of the output that we produce. So the running time should depend only on the size of the output. So let's define that more properly. So let's say we have a cluster A, and we have a random vertex V inside A. So we don't know A, so we have a random vertex inside A, and we just see V, and we want to find A. So we can do some local random walk around V maybe. So we may end up computing another set S, which is similar to A, but not exactly A. And we want to make sure that the conductance of this cluster is as small as possible. So if I want to do something like this, can I achieve logarithmic approximation? The answer is no. If I want to do it only local, can I achieve something like spectral clustering, square root of the optimum solution? The answer is yes. So it's possible to design local algorithms with running time as a function of the output size, with good conductance. So now I want to tell you what is if I want to go beyond conductance, I have to basically revise this notion. So conductance captures the cut value over the volume inside. So a good cluster has some has good conductance. But if you notice here, there is another cluster like the one that I draw here. This one has only one edge going outside. So it has good conductance in some sense. So is it a good cluster? No, because there is a cut that can divide this cluster into two pieces. So in particular, maybe we want to find clusters with good conductance, but also with good connectivity. And by connectivity, we mean the minimum conductance of a cluster inside the cluster. So basically, we are looking for clusters with the small conductance. And at the same time, we know we don't want our clusters to have a small connectivity, because that will mean that translates to poor connectivity inside. So we want to make sure that we get rid of this type of clusters with poor connectivity inside. So good cluster is like a cluster with a small conductance and large connectivity. So the first thing I want to mention is there are very local algorithms that achieve good connectivity and good conductance at the same time. So assuming that there is a gap between the internal connectivity of the cluster and the external connectivity, so what I call gap of A here, assuming that we have a big gap between this internal connectivity and external connectivity, I want to output a cluster with good conductance. And like with the assumption that there is a big gap, there is an algorithm that that achieves a very good approximation based on local random walk, local PageRank random walk. And this is like a result that was presented in ICML. And I'm going to tell you briefly like what the algorithm is. So my goal is to find a local random walk algorithm with good connectivity and good conductance. So what is the algorithm? The algorithm is basically, we start from node V, and the first step is to compute the personalized PageRank vector from node V with some restart probability to all other nodes. So this is basically the same PageRank random walk that you know, but the restart is only at node V. So from node V, we compute this vector. We first normalize it with the degree of each node, and that will be a normalized personalized PageRank vector. So then we sort vertices based on basically their decreasing normalized personalized PageRank. And we can show that there, like if I pick one of the prefix cuts like this cut will have good conductance and good connectivity at the same time, assuming that we have a gap. So in particular, I can look at this vector and I can find where it drops fast. And that place that it drops fast will give me a good cut around that node V. And I can provably show that this, the conductance of this cluster is very good compared to the optimum conductance. So why is it practical? Because this algorithm is very practical local because one can compute these approximate personalized PageRank vectors using local random walk algorithms with some precision. So the precision epsilon here is like the additive error that when we decrease epsilon, the number of vertices that will have non-zero personalized PageRank will grow. So computing this personalized PageRank vector is very simple using some push flow algorithms, and you can find order k top personalized PageRank numbers using order k push operations, push flow operations. Just to show you how simple is basically to write like a program to compute a push flow. This is basically a local push flow algorithm from one node. Basically, at each step, it pushes some amount of flow to its outgoing neighbors, and then it keeps some residual part for the personalized PageRank of a node itself. So it can be very easily implemented in MapReduce or Pregel like to find these local clusters. So, and we can basically compute for any type of graph we face, like using maybe hundreds or thousands of machines. Like in parallel, we can compute all these local good clusters because we use local algorithms. So now we have these local algorithms and local clusters, and we want to go from these to overlapping clusters. How do we do that? We see that there may be too much overlap in these clusters that we find. The next step is to merge clusters that have very large overlap. So what we do is we construct a graph over these clusters, and we put an edge between two nodes if their clusters have a big overlap. So now the question is how to cluster this new graph. And that's now a global clustering problem, but because we fine-tune like the local cuts, we know that when we find a good clustering of this graph, the cuts that we have in the global clustering is also very good. So I want to basically tell you about how we do hierarchical clustering on these graphs. But in order to simplify matters, I'll tell you how we do like connected component computation, which is the simplest clustering method for these graphs. So we build on like this work of Rastogi et al., and where they do connected component in MapReduce. So if you want to compute connected components in MapReduce, what you can do is you can keep track of like a component or a state for each node. And you can apply different type of algorithms. For example, the hash min algorithm, what it does, it keeps track of the minimum ID of the cluster it belongs to, and it basically propagates this to the neighbors in each round. The hash to all node keeps track of the whole connected component, and it reports that to like the neighbors in rounds of MapReduce. The hash to min algorithm, what it does is it sends the min ID to the all nodes in the cluster, but then it sends the whole cluster or the whole connected component to the min ID in each cluster. So these algorithms differ in terms of the number of rounds of MapReduce they take, and also in terms of the communication they have in each round. So in particular, so like if you look at the performance of these different type of algorithms, you see that the number of rounds like improves from like the simple hash min algorithm to hash to min or hash greater to min algorithm, but then the communication may increase. So what they have in that paper is they reported the best algorithm is hash to min, where basically they have like a relation between the min ID and the whole component. So first thing we did, the first idea was to change this algorithm and apply what we call alternative hash greater to min and hash to min type algorithm to improve the number of rounds. What we can get is like on several graphs with trillion edges and public graphs with 10 billion edges, we can get 2 to 4 times faster than our own implementation of hash to min, like based on the new algorithm. And then we see that it takes 5 to 22 rounds to compute connected component on these big graphs. So now the next idea was to improve this number of rounds that we get by using like in-memory service. So we like there is a SSTable service that we can use to load like part of the data, or basically after some number of rounds, what we see is that the number of active components in the connected component, like in the connected component, the number of active IDs like decrease drastically, so we can fit it in memory. So what happens is that if we do that, we can like save many rounds of MapReduce by doing in-memory operations, and we can maybe basically do connected component computation for all of these graphs in 3 to 5 rounds, and like 4 to 15 times faster than the hash to min type algorithm that we had. So that's the second idea. The third idea is was to basically apply a new asynchronous message passing framework that we have used for several applications, including the connected component application. So here we keep track of a small state for each node, and we communicate the min ID that nodes have seen so far. But we do it completely asynchronously. We do this by keeping track of having basically a priority queue on each machine. And after like the priority queue decides to send a message from so nodes keep putting messages in the priority queues, and priority queues decide to send these messages in batches to other nodes in other machines. So the fault tolerance that's also implemented in this framework is kind of asynchronous checkpointing, which is very fast and very like scalable. So with this, we can handle any type of graph that we have seen at Google, at least, for computing connected component and this type of hierarchical clustering. It's we get like 25 to 40 times faster and more scalable like code compared to the same to an implementation of the best algorithm we know of inside Google. So we re-implemented this ICD paper algorithm, and we compare ourselves to that. So with that, and we get like 4 to 6 times faster than the best pure MapReduce implementation that we have. I wanted to tell you like the final result when we put all these things together. So maybe I guess I'll just show you that like when we apply these, like finding local clusters and then combining them using connected component and clustering. So I can just show you that in terms of the mean conductance of the clusters, after this post-processing operation, we don't lose much. And even though we don't have a proof, end-to-end proof, that shows that like these algorithms achieve good conductance cuts overall, but we know we don't lose much in the second step, and we know that the first step we found good conductance cuts. So by that, I conclude, we are working on applying this asynchronous message passing time framework to develop other algorithms. I can tell you more offline. I'm out of time. And yeah, improving the MapReduce-based algorithms for clustering and finding more theoretical and practical results at the same time. Thanks.